Okay, infinite solutions, and how many pivots do I have? 2, which means I have 2 free variables. That's a t and that's an r. So my x1 is equal to negative 3t plus 4r plus 5. My x2, oops, is a free variable. So x2 is equal to t. Again, just to point out, a lot of you on your test 1 just left that matrix as your answer. If it says solve the system, the matrix is not your answer. You need to actually write out the answer. That's what I'm doing here. So x3 is equal to negative 2r, and x4 is equal to r. Oh. Okay, what is this the equation of? Yes, perfect. Good job. Good job, Nathaniel. How many parameters are there, guys? 2. And 2 parameters means what shape? A plane. So this right here means that the intersection of what we started with, which was rectangular prisms in this case actually, is a plane. So here I could even add, if I wanted, intersection is a plane. And we do not have to do this, but we might want to write the vector equation as well now that we know how to do that. My point would be 5, 0, 0, 0 plus my t vector plus my r vector. And based on what we've been learning recently, we now also have a basis for the null space. The basis for the null space is negative 3, 1, 0, 0, 4, 0, negative 2, 1. So the basis for the null space of the coefficient matrix is those 2 vectors that show up in the vector equation. Okay, are there any questions about the row reduction? Hopefully an easy 8 points. Fingers crossed that that's an easy 8 points for you guys. But you need to remember to actually write down the answer. Don't just leave me a row reduced matrix like a lot of you did on test 1. Okay, question 2. You guys' favorite type of question. Does anyone need more, does anyone need to keep seeing what I just got rid of? You got it. Find the value of k. The sarcasm being about everyone's favorite question. Yes, that was sarcasm. Nobody likes these questions. But like, that's normal. Everyone hates these questions every semester. So we're looking for h and k such that if it doesn't specify to write if it's a plane or a line, leave it in parametric form, but I will tell you that it does specify. So you're gonna need to write that tomorrow. So A, infinitely many solutions. B, no solution. C, a unique solution. Daniel, I don't remember, it's either 21 or 22. What I did is I took an old final from a long time ago. The class has changed a little bit, so I took off the problems that had changed and replaced them with problems that are more similar to the stuff that we do, and then I got rid of 2 questions. So really, it's like an old final. So it's really the length of the finals that you should hopefully be doing now. And I will send an MIO. Yeah, so Parth, I mentioned that in class, that a lot of times one of the determinants for Cramer's rule is given. So you should always pay attention to that, because sometimes it is, but sometimes it's not. What do you mean they usually make it shorter? Like if you think about on the test, no, it's normally, they do not normally make it shorter, no. But like they'll do things like maybe give you one of the determinants for Cramer's rule and then ask you another determinant question later, as opposed to having two determinants in Cramer's rule. So like sometimes you see that. It's I can't remember if it's 21 or 22 questions. I think it's 21 if I'm not mistaken. Okay, so here we want to find H and K such that this has infinitely many solutions, no solution, and a unique solution. So a thing that I've noticed that you guys like to do in class is partially row reduce and not finish row reducing, and then just write random numbers. It is possible if you think there were. I haven't actually looked at the May 2019 final, so I don't know. But if you think there are, you can send me a message and ask, and I'll let you know. Okay, so you need to show your work. You need to explain things. Now, a great way to explain things, to start off by explaining things, that's not going to be fully explained, but a good way to start explaining things would be just right over here, write what each of these things mean. This means consistent. So consistent means no contradiction, and at least one column without a pivot. This no solution is when we have a contradiction. So in this case, that's going to be zeros on the left side and not 0 on the right side. Note that this, for example, is that a contradiction? The second thing that I wrote there? No, that is not a contradiction. Good job, guys. So then a unique solution, in this particular case, this is a square matrix. Our coefficient matrix is square, so a unique solution just comes from a pivot in every column. We don't have to worry about there being a contradiction, because there's not going to be, if there's a pivot in every column, there's not a possibility of a row of zeros. So this is just pivot in every column. So we're going to start off by row reducing. I'm going to do row 3 minus 8 row 1, which will give me 1 0 0 3 2 4 1 1 8. So then 14 minus 24, that gives me a negative 10, and then k squared minus 4k minus 15 minus 16. 2h plus 3 minus 32. So I'm going to write these down just because sometimes you guys have trouble with these. So this is k squared minus 4k minus 15 minus 8 times 2, and 2h plus 3 minus 8 times 4. Yes, your answer will have both h and k in it. Now, sometimes h isn't going to matter, and you'll need to say that. Okay, so this is still not Rref. So now we have our new pivot of 1 there. And we're going to do row 3 plus 10 row 2. Do I need to make that 3 a 0? No, I just need Rref for these problems. Would it be incredibly inefficient to do that extra step of making 3 a 0? Yes, it would be, right? That's like this extra step, all these extra calculations you would have to do that are just totally unnecessary and would take you time. So we only need Rref here. So we're going to say then 1, 0, 0, 3, 1, 0, 2, 4, 1, h. And I'm going to do these calculations with k and h down on the bottom again, just so that you guys can get comfortable with them. So this is k squared minus 4k minus 31 plus 10 times 1, k squared minus 4k minus 20 plus minus 21. Now I'm going to go ahead and factor this while I'm at it, because it's usually, we want this in a factored form here. That's going to help us to see where this thing equals to 0. So I'm looking for two numbers that multiply to give me negative 21 and add to give me negative 4. So that's going to be k minus 7 times k plus 3. Well, they're 21. So, but if you think about this one, like if I'm looking at the two numbers, right? So if I have negative 21, what two numbers could I multiply to give me that? Well, 1 times 21 and 7 times 3. That's it. Those are the only two possibilities I have to think about in my head, right? So clearly it's not going to be the 1 times 21. So then it's just a question of which one of the 7 and 3 needs a negative. Because 21 minus 1 is 20. It's not even close to 4. Whereas 7 minus 3 is 4. But I want a negative 4, so it's going to be 3 minus 7. In this case, it was straightforward because 21 really only has 2 prime factors. There's not like, it's not like with, I don't know, like 18, where I could be like 9 times 2 or 3 times 6. Do you see what I mean? Okay, so then also we have 2h minus 29 plus 10h. So that gives me a 22h minus 29. Okay, so that's what goes right here. All right, so what do you guys think? And by 22, I mean 12. Yes, thank you, Nick. I can add 12h. So we have 12h minus 29. Now, the first thing that we want to do is look for an obvious contradiction. So we always start by saying, is there an obvious contradiction? And an obvious contradiction would be what occurs when you have a row of zeros. Contradiction. So it would be like 0, 0, 0, question mark. And in this case, there is no row of zeros. So then we're going to identify k's that are in pivot positions. If it's not in the pivot position, I don't care about it. So like this h right here, is it important to me? So Daniel, what I mean by obvious contradiction would be if I had like an extra row here, oops. Like if I had an extra row here that was like 0, 0, 0, h plus 4, right? Well, the obvious contradiction would be when h equals negative 4. So we still are going to care about the other things in the case when h does not equal a negative 4. Does that answer your question? If that happened, well, first of all, it's not going to happen in these problems because it would kind of make the problem way too easy. But yeah, if that happened, if you were just like 0, 0, 0, 3 here, then there's nothing to do. The answer is it always has no solution. That said, that's never going to happen, right? Like, so when we're looking for an obvious contradiction, we're not looking for that because that's not going to happen in these problems. Unless I like screw up the problem by accident. Okay, so then the next thing we do is what causes 0? What h or k value causes 0 in pivot positions. And this would be when k minus 7 times k, Adam, that is an answer to one of the three things. K plus 3 equals 0, k equals 7, k equals negative 3. So what this tells me, is that when k is not these things, there is a unique solution. When k is not these things, I have a pivot in every column. So Nick, I'm not sure I understand your question because we haven't like actually made an answer yet, but sometimes there are going to be two values that cause zeros in pivot positions, yes. So now for these things right here, a good plan for showing work is to plug them into the matrix. So we're like, what is happening when k equals to 7? And what's happening when k equals to 7, I'm going to plug this into my matrix, and I get 1, 0, 0, 3, 1, 0, 2, 1, 0. And then 4h, 12h minus 29. And here we can see that this depends entirely on this value right here, right? We have this obvious contradiction. So if k equals 7, so we can have infinite solutions here, or we can have no solution depending on that value of h. So here, this is going to happen if 12h minus 29 equals to 0, and no solution will happen if it does not equal 0. And then we'll plug in k is equal to negative 3 as well, and see that we actually end up with the exact same matrix. So now we have all of the information to make our conclusion. Our A was infinite solutions, I believe, wasn't it? Our A was infinite solutions. And infinite solutions happens in two different cases. When k is equal to 7 and h is equal to 29 over 12, or k is equal to negative 3 and h is equal to 29 over 12. B, my no solution happens. Was it no solution B? Yeah, my no solution happens when k is equal to 7 and h does not equal to 29 over 12. Or when k equals negative 3 and h does not equal to 29 over 12. Yeah, that's fine too, Adam. And then my C is what happens, the first thing we figured out, one solution occurs when k does not equal 7 or negative 3. Does h matter? No, and it's important to include that in your answer. H doesn't matter. And this is my final answer. Whew. Are there any questions about this? Okay, are you guys ready to move on to the next question? Okay, so the next question is a word problem. Mark, you're using the same paper for test 3 that you used for the final. So when I did it for test 3, I was counting that for both the test 3 and the final. So I'm not going to have you guys reconfirm it. I'm going to just have you use the same thing. And to continue answering that question, I will also be sending you an MIO later today, letting you know exactly about timing and things like that. Part the answer is because one semester they decided they were going to get rid of one of the word problems so that they could ask more theory questions. So that they could ask more theory questions. You can expect all of the word problems to be there. And then wait, Adam asked a question about the difference between Leontief or simplex. Well, simplex will tell you to set up the linear program, and it will ask you to maximize or minimize. Whereas Leontief will ask you to find the output necessary in order to meet demand. So the two questions are different. Simplex will be maximize. Leontief will be find the necessary output to meet demand. And Leontief will also ask you to find a consumption matrix, while simplex will ask you to set up the linear program. So I have given you massive amounts. So the ones that are posted on Leia for your bonus question, I'm expecting you to write on loose leaf, but for the final itself, you can do either. You can write on loose leaf or on the paper. Normally when you have the final in person, there's lots of space for every problem, and I've made it such that there's just massive amounts of space for every problem. Okay, so next question here is 3. And so this question is really quite important because when we look at it, you'll notice that we learned it in class, but it actually didn't show up on any of your in-class tests. So you can bet that it's going to show up on your final. Do you guys have something to read it, or do I need to share my computer screen to show it to you? If you don't have it, let me know. If you do have it, please read it. And when you've read it, please let me know in the chat. Okay, so the first question here is define your variables and set up the system needed. Okay, so this problem is actually similar to simplex, and it really, like, the setup for this problem is actually going to be exactly the same as the first simplex word problem, except instead of having inequalities, we have equalities. So with that said, on your test yesterday, the first part of the simplex question was set up the variables and create a linear program. And many of you just like immediately put it in a matrix. A linear program, I remind you, so you should have this definition in your notes, like with the big thing circled by it, is the set of inequalities. So when this says set up the system, I need the actual like system of equations, not just a matrix. Same with simplex, I don't need just a matrix, I need the actual system of inequalities. Okay, so here we kind of have two things going on. We have cardigans, sweaters, and dresses. And we have Iceberg yarn, nutmeg yarn, and charcoal yarn. Which one of these things is going to be my variables? I don't think we'll finish before 12. I'm gonna do my best though. If it seems like I'm not gonna finish, I'll probably like in the last 40 minutes or so stop doing it and ask you guys which ones, like which questions that are left you would prefer me to do. Okay, cardigans, sweaters, and dresses are my variables. Good job, Nathaniel. Why are cardigans, sweaters, and dresses my variables? There are two clues. One, I'm given totals. My totals are for iceberg, nutmeg, and charcoal. My total iceberg is 84, my total nutmeg is 72, and my total charcoal is 24. So when I'm given totals, that is definitely not my variables. Second, the question says, help the guild determine how many cardigans, sweaters, and dresses they can make. I want to know how many cardigans, how many sweaters, how many dresses. So the thing I want to know, that's my variables. So here I have set up my variables. So this is the first part of part A. And the second part of part A is going to be to write my system of equations. Now remember, the equations, for each equation, I'm going to be thinking about the totals, okay? So I'm actually going to set up here so that I have X, Y, Z. I'll kind of set up a little chart here, and then I'll have my totals, and they're 84, 72, 24, and I'll have iceberg, nutmeg, and charcoal. And then you'll notice that usually these things go into the matrix in columns. So this tells me each cardigan requires 6 iceberg, 3 nutmeg, and 3 charcoal. So that'll be 6, 3, 3. Each sweater requires 5 iceberg, 5 nutmeg, and 1 charcoal. And each dress requires 6 iceberg and 8 nutmeg. Okay, again, this chart is not my system. This is not equations. I need to write these as equations now. Are there any questions about how we made this chart? Good. So then my system of equations that I'm asked to set up is 6x plus 5y plus 6z is equal to 84. 3x plus 5y plus 8z is equal to 72. And 3x plus y is equal to 24. So this right here is the second part of my answer to A. Now for B, I'm told that after I row reduce, I will end up with this. And we call this x, y, and z, so I'm just going to change these things. X is equal to 4 plus 2/3 t. Y is equal to 12 minus 2t. And z is equal to t. This is a realistic solutions word problem. So the very first word problem we learned, actually. So if you look in your notes, it'll be like under realistic solutions. And again, I stress, this didn't show up on any of your in-class tests. So you can bet it's going to show up on your final. Okay, so now it's asking me to find the realistic solutions given this. So do you need to row reduce? No, the row reduction is done for you. The solution is given to you. So now I just need to find out which one of these solutions makes sense. Then that means you'll only have 2 equations and not 3 equations, Adam. So if you only have 2 totals, like if there were only iceberg and nutmeg, that third equation just wouldn't even be there. Okay, so now for my realistic solutions, I know that I'm not going to make half a cardigan, so I can have no fractions, and I'm not going to make a negative amount of cardigans, so I can't have negative things. So we start off with, we want each of these things to be positive. And I'm going to go through and deal with each of them. So I want to find t so that x is greater than or equal to 0. Okay, so that means I have 4 plus 2/3 t is greater than or equal to 0. Let me make sure that I wrote this down correctly. I did. So this is saying 2/3 t is greater than or equal to -4. So t is greater than or equal to, be careful when we have a fraction, we flip the fraction. So I'm multiplying by 3/2. So t is greater than or equal to -6. That's my first restriction on t. I know it has to be bigger than -6. Then I'll go to y greater than or equal to 0. And that's 12 minus 2t is greater than or equal to 0. So that's minus 2t is greater than or equal to -12. So then I divide by -2. What is division or multiplication by a negative number? You got it. It causes my inequality to flip. So this becomes t is less than or equal to +6. So right now I have t between -6 and 6, but I also have to look at my z value. And z is just t is greater than or equal to 0. Usually there will be one of the inequalities that's kind of useless. Oftentimes it will be the t greater than 0 one. What is it in this case? Which inequality do I not need to look at anymore? So I have t greater than -6, so that gives me a lower bound of -6. Then I have t less than or equal to 6, that gives me an upper bound of 6. Then I have t greater than or equal to 0. You got it. So that -6, that was my first lower bound, now gets moved to 0. It turns out that this one is kind of useless. So what I have here then is 0 is less than or equal to t is less than or equal to 6. But then we also have to think about the fact that we don't want any fractions. So now I can say t is equal to 0, 1, 2, 3, 4, 5, 6. Are there any of these that I can get rid of that would also cause fractions? You got it, Parth. Good job, Daniel. So that 2/3 over there tells me to get that I can only keep multiples of 3. So I'm going to get rid of 1, I'm going to get rid of 2, I'm going to get rid of 4, I'm going to get rid of 5. So this is not my answer. T equals 0, 3, and 6 is not my answer. It says find all of the realistic solutions. The realistic solutions is going to be the number of cardigans, sweaters, and dresses. So t equals 0. When I plug that in, I'm plugging it into my original general solution. So this is the general solution. Note, a general solution and a general equation are not the same thing. You guys need to know the difference between general solution and general equation. Okay, so t equals 0, I plug this in and I get x is equal to 4, y is equal to 12, and z is equal to 0. Then t is equal to 3. which I plug in and get x is equal to 6, y is equal to 6, and z is equal to 3. So we know that it's 0, 3, and 6 because greater than or equal to 0 gave us that it had to be between 0 and 6. But the fact that there was that 2/3 there in my general solution told me that I only wanted to keep multiples of 3, that everything else would cause fractional answers. Okay, good. So then I'm gonna plug in 6, and I'm gonna get 4 plus 4, that's 8. Y is equal to 0, and z is equal to 6. Now we always wanna connect this back to the original problem. So we had cardigans, sweaters, and dresses. So it's 4 cardigans, 12 sweaters, and 0 dresses, or 6 cardigans, 6 sweaters, and 3 dresses, or 8 cardigans, 0 dresses, and 6 sweaters, and 0 dresses. So cardigans, sweaters, dresses. So to connect it back, I'm just going to write that on the side here. Because sometimes these problems can have a lot of words if you try to write all of them. Okay. Are there any questions about this problem? Just going to write the matrices for 4 down really quickly. I am going to ask you in half an hour if you want one. Okay, so 4 has brought us into, so the first part, that first section was really just like linear systems. So that was understanding how to solve linear systems, understanding applications of linear systems, and now we're moving into the matrix operations section of this final. So we're given a bunch of matrices, and we're given some stuff, and we want to find specific things or state that there's no information. So the first thing we want is C transpose B. Before we just write out matrices and waste our time writing things when we might not need to, we should start off by figuring out if it's even possible. What size is C transpose? You got it. C transpose is 3 by 2. So C transpose is a 3 by 2 matrix. What size is B? 3 by 3. Is this possible? Can I multiply these two things together? Nope. So these two things right here, that 2 and that 3, they are not equal. So this says, find the following or explain why it is not possible as appropriate. That right there that I just wrote is a good explanation. So we would write that, and then we would just write not possible. But both of those things are important to the answer. That's the answer, that's the explanation. Then it says a matrix X such that AX equals D. I actually have two ways that I could solve this because of the size of D. So my option one would be to treat this as a matrix equation. And we would say that X is equal to A inverse D. And my option two would be to row reduce. And this is only an option because D is a vector. In other words, D is a 2x1 matrix. We're going to go with the solving the matrix equation because that's usually faster. And because it works every time A is invertible, whereas the other one only works in this specific case. So A inverse D, the first thing we want to do is find A inverse. And this is a 2x2, which means that the inverse is going to be pretty straightforward. We have our formula. So A inverse is equal to 1 over the determinant. So that's -6 plus 5. I flip these two, and I multiply these by -1. Okay, now 5 minus 6 is -1. So I just distribute the -1 to the inside to get that A inverse is equal to -3, 5, 1, -1, 2, which would mean that X is equal to A inverse times D. And then this becomes now matrix multiplication. So I'm doing -21 plus 40. And then I have -7 plus 16. So X is equal to 19, 9. And that's my final answer to B. It doesn't change much on each 26. You got it. Okay, C. We want the determinant of AC. Well, what size is A? That's 1 over the determinant, Kyle. So the determinant, remember the determinant of a 2x2 is this diagonal minus this diagonal. So I just did -2 times 3 minus 5 times -1. Okay, good. So A is 2x2. We always start off by thinking if it's possible. What size is C? Two by 3. So can I multiply those together? Should I? So no, I should not, because what size is AC? The 2's in the middle are equal, and remember, we look at the outer things to figure out what the new size would be. AC would be 2 by 3. Can I take the determinant of non-square matrices? Nope. So we can't, so it does not make sense to waste our time multiplying them together when we see that the size would give us something that doesn't have a determinant. So I can only find the determinant of square matrices. This is not possible. Oops. Which brings us to D. Which tells me to find B inverse. Yes, we can only do the determinant of a square matrix, right? Because we know if it's not square, it's not invertible. It's not like we think about non-square matrices differently. Determinants only work for square matrices. Exactly, I can only do the inverse of a square matrix as well. Now, B is a square matrix. I'm asked to find the inverse. Where is B? Yeah, come on. There it is. Okay, so I'm asked to find the inverse. So really I have two options here. Yes, I am scared. I have two options here. Well, actually I have three options. I could start off by taking the determinant to see if it's invertible. But if it is invertible, then I'll still have to do the inverse. I could find the adjoint. Yeah, I could do the 3x3 trick to check the determinant. But again, like that's an extra piece of work in a sense, because if the determinant is not 0, then I still have to go find the inverse. And so the work that I did would be work that I could have done towards finding the inverse anyway. So the most reasonable way to approach this problem would be to stick it in a matrix and start row reducing and just see if it reduces to I, right? So we're gonna like augment with I and we're gonna do that step to see. That said, starting with the 3x3 trick and seeing if the determinant's 0, it's not wrong. It couldn't hurt to do it. It just might take a little extra time if in the end it ends up being invertible. So what I'm going to do is I also could find the adjoint. And when I find the adjoint, that would give me a way to find the determinant, which would then allow me to see if it's invertible. And the adjoint gives us another way to find the inverse. I'm just going to remind us that the first way we learned to find the inverse was this. 1, 2, 5, 4, 9, 17, 1, 1, 8, 1, 0, 0, 0, 1, 0, 0, 0, 1. And to row reduce. So I'm going to do row 2 minus 4, row 1. And I'll do row 3 minus row 1. And that'll give me 1, 0, 0, 2, 5, 1, 0, 0. Then 9 minus 8, that's 1, 17. Minus 20, that's negative 3. And then minus 4, 1, 0. And then 0, 1 minus 2, that's negative 1. 8 minus 5, that's 3. 0 minus 1, that's negative 1. 0. 1. Adam, it's not letting me do it. Yeah, okay. I'll look at it in a minute. I can't look at it easily. Okay, so what I see here, what's happening with row 2 and row 3? What's going on with my second row and my third row of A? They're multiples. And if 2 rows or columns are multiples, what's the determinant? 0. Is this going to reduce to I? It won't reduce to I. Plus, the determinant of B will be equal to 0. So the answer here is that B inverse does not exist, right? So had we found the determinant, we would have seen it was 0, but notice that this also took us one step, but it was one step towards finding the inverse in the case that it ended up being invertible. B inverse is undefined. All right, 5. Any questions about 4? Absolutely. Like if you wanted to right here, if you're still unsure, you could keep going and you could be like row 3 plus row 2. And then you would be like 1, 2, 5, 0, 1, negative 3, 0, 0, 0. Oh, do you see what I mean? So like if you did that one extra step, it's not a problem. No, you would not lose marks for that. Because that's you doing an extra step just to make sure to make sure that you understand yourself. It's not you completely ignoring all of the methods we've learned to make things easier. Yes, I think I will have the marks this week. The sooner I get it over with, the sooner I can have a break. So I'm sure you guys feel the same way. Okay, so 5. Here we're given A, but we're not given the last row of A. And then we are asked to find the matrix multiplication A times the adjoint of A. Do we have a formula that tells us this? This is a formula that I've been trying to like get you guys to use in different ways throughout the semester. What is the A times the adjoint A? What should it equal? Yeah, part. So not the determinant times the inverse. So if the formula that you've memorized, some of you have probably memorized that A inverse is equal to 1 over the determinant of A times the adjoint of A. But we actually saw this formula in about 3 different ways, and I told you you really need to be comfortable either with all of them or with matrix equations and solving for them. So in this case, I can actually see that A times the adjoint of A is equal to the determinant of A times I. And this one I've had you use on a lab before, for example, to do determinants. So I know that when I multiply A times the adjoint of A, I should end up with this. So in other words, I should end up with a matrix that has the determinant times the diagonal and 0 everywhere else, which means I only need to find the first number when I'm doing the multiplication. So in other words, I can say A times the adjoint of A is equal to 1, 8, 2, 5, 5, 3, question mark, question mark, question mark. And it doesn't matter that I don't know what those questions are, because when I multiply these things together, I actually just have to do the first row times the first column. And I will get 10 minus 8 times 13, that's 80, minus 104. Plus 10. And that's it. I don't have to do the second thing. I know it's going to give me 0. I know it's going to give me 0. I know this is going to give me 0. I know this is going to give me 0. 10, so that's 20 minus 104, that's negative 84. which means that that negative 84 is also going to be down the diagonal. So A times the adjoint of A is equal to negative 84, 0, 0, 0, negative 84, 0, 0, 0, negative 84. And this is really relying on your knowledge of the formula that relates A inverse and the adjoint of A. Are there any questions about what we just did here? Okay, so then the next question is, what's the determinant? Well, what is the determinant of A? You got it, Kyle. Negative 84. I don't actually have any more work to do. I already did A times the adjoint of A. I can see that negative 84 down the diagonal. That's my determinant, which is good news because I don't have all of the rows of A. So there's no possible way that I would be able to actually use cofactor expansion or row operations to find the determinant here because I'm missing a whole thing. There's not a specific reason. It was totally random. I really like the number 8. So 2018 seemed like a good one. Okay, 6. So here we are given that the determinant of A, B, C, D, E, F, G, H, I is equal to 6. And for A, we are asked to find this new determinant. So we are asked to find the determinant of 3A, 3B, 3C, G plus 2A, H plus 2B, I plus 2C, negative D, negative E, negative F. Where's a good place to start? What should I do first? So remember, our goal is, that's a great place to start, Daniel. Our goal is to row reduce this thing to get it back to the first one. So getting rid of the 3 on the top is good. Doing row 1 minus row 2 is actually a bad plan because row 1 minus row 2 would be like 3A minus G plus 2A, and then suddenly my row 1 would be A minus G. And that really didn't get me anywhere. It actually made things more complicated. So getting rid of the 3 and the negative 1 on the bottom is a great place to start. I'll do row 1 times the third and row 2 times negative 1. Does that change the determinant? Exactly. So we're going to undo the things we did. So I'm going to put a positive 3 out front and a negative 1. So doing row 2 times negative 1 is also not really useful at this point. And we'll see why in just a second. So this gives me A, B, C, G plus 2A, H plus 2B, I plus 2C. Oh, I see what you mean, row 3, my bad. D, E, F. Okay, now be careful because what I noticed on the labs and on the test from a lot of you is that you were like doing row reduction, but you weren't realizing that the matrix that you're writing there with those things, it represents a number itself. We're trying to get it back to the original matrix we started with so that we're multiplying by 6 at the end. So now I have my ABC, I've got DEF. Daniel, no, we're gonna do where nothing changes in just a second. If I multiply by a whole number, like if I multiplied by 5, then I would have to undo it by multiplying by 1/5. Okay, so what's a good next operation here? row 2 minus 2 row 1. You got it, Adam. So I'm going to do row 2 minus 2 row 1, and that's going to get rid of the ABC there. So this 3 and this -1 are still out front. It's almost like I'm creating equations. The arrow could actually be an equal sign. So this will become A, B, C, G, H, I, D, E, F. And did that row operation change the determinant? No. So we should make a note of that. You can't just do it and not tell me what's happening. Tell me what's happening, right? No change. Be like, oh, hey, I know that row operation doesn't change my determinant. So I'm going to tell my teacher so that she knows I know. Did I get this back to the original thing? Is it the original? Are you sure? Exactly. Good job, Jordan. I'm going to have to switch rows 2 and 3. So rows 2 and row 3 will switch. And when I switch those rows, exactly. So if I multiply through by, so we have 3 row operations. We have, well, actually, I'll talk about it as soon as we're done because I'm going to have done all 3 of them. If I switch rows 2 and row 3, does that change the determinant? Yes, it multiplies it by another -1. So I'm going to have a -1 out front, 3, -1, and then I will have A, B, C, D, E, F, G, H, I. And what does this equal? What's this equal? You got it. So that's equal to 6, which means that my final answer is -1 times 3 times -1 times 6, which is 18. And that is my final answer. So I've noticed that a lot of you were answering in the beginning, but a lot of you that were answering in the beginning have stopped answering. Just so that you know, what I'm going to do at the end of this is I'm downloading the chat and I'm going to go through and see that people were really participating actively throughout the whole thing when it comes to giving you your bonus points. So just know that I will be looking back at the chat to make sure that you were participating if you want your bonus points. Okay, so is that clear to everyone? Okay, so note that we have 3 row operations, just because someone asked this question. One is I can multiply a row by a non-zero constant. That changes the determinant. Those are the first 2 things we did were that. So we changed the determinant by multiplying by 3 and -1 outside. The second row operation is we can add a multiple of one row to another row. That doesn't change the determinant. So like row 2 minus 2 row 1, we're good. Row 5 plus 7 row 1, we're good. There's no change. And then the third row operation is switching 2 rows, and that multiplies the determinant by -1. Okay, B here. So my B is A plus 3D, B plus 3E, C plus 3F. Actually, I'm going to do this column by column so that I have space here. Yes, Nathaniel. So with determinants, we can also do the transpose, and that will not change the determinant. So sometimes we might have to do the transpose as a row operation along the way, even though that's not a row operation that we can do with like in normal life, in normal row operation. But if we're taking the determinant and we do the transpose, nothing changes, and so that's fine. Okay, what should I do first here? Suggestions. So they are sort of multiples. Not quite yet, but there's something I could do to make them clearly multiples. Exactly. If I do row 2 minus row 3, then suddenly I can see those multiples really easily. So row 2 minus row 3. I can't just take the 3's off because it's not like everything is multiplied by 3. I have a plus 3d. So it's not that a isn't multiplied by 3. I have that plus there that stops me from doing that. So here I have a plus 3d. Now this will also be a plus 3d, and then that will still just be g. And now this will be b plus 3e. This will be b plus 3e, and now this is h. C plus 3f, c plus 3f, and now this is I. What's this equal? You got it. It's 0 because 2 rows are multiples. Okay, so it is almost 10:30. I'm gonna do the next problem, and then do you guys want a break today? Or do you want to just like power through and try to finish this thing? It's up to you guys. So I have 2 votes for breaks and 2 votes for powering through. Good news. Okay, it seems like most of you want breaks. So those of you that voted to power through, I'm sorry, we will take a 10-minute break, but we'll do our best to get through as much of this as possible when we come back. So it'll be just like 10-minute break. Sound good? Or we could even say 8 minutes. Give me time to go like run down the block and come back, just to get some air. That's fine, Daniel. We're gonna do Kramer's rule, so if you're comfortable with that, that's fine. Okay, so 7 is now some true-false questions. So here we have that A is 5 by 5, and the determinant of A is equal to 0. So true, false. So A, here we're told that the determinant, oh, I'm sorry, the determinant of A is equal to 10, my bad. And then this is true, false. The determinant of A transpose is equal to 1/10. Is that true or false? I actually just answered this question in words a few seconds ago. So is this going to be true or false? Why? That is correct, Adam. Good job, Jake. We got there. Determinant of A equals to the determinant of A transpose. We just said a few seconds ago that doing the transpose does not change the determinant. This is false. And it's because the determinant of A is equal to the determinant of A transpose. So the determinant of A transpose would be 10. So someone, I think it was Adam L, said that would be for the inverse. That is correct. The determinant of A inverse would be 1/10. The determinant of A inverse would be 1/10. Now for B. The columns of A, oh, it was Adam I, sorry. The columns of A are linearly independent. True or false? If the determinant is 10, You got it. It's true. And what would be a good explanation for that? You got it. Oh. So exactly, it's invertible, it reduces to I, and there's therefore a pivot in every column. And that's because the determinant of does not equal 0. Okay, lastly, C. The determinant of 2A is equal to 20. Exactly. If the determinant was 0, it would be linearly dependent. Good job, Daniel. This is false. And why is it false? Saying what the determinant of 2A actually equals to would be a great explanation. So this is false because the determinant of 2A actually equals to what? Exactly. We have to put that 2 to the power of 5 because it is a 5 by 5 matrix. So it equals to 2 to the 5th times 10. So it's actually 320. Okay, so we're gonna pause the recording. Kramer's rule. Let's do this thing. I went for like a run down the block just to like get outside, and now I'm basically. Okay, so here we are told that the determinant of A equals 0 for this system. So I have x1 plus 2x3 plus 3x4 is equal to 2, negative x1 plus 10x3 is equal to 5, 5x1 plus 2x2 plus 4x3 minus x4 is equal to 3, 3x1 minus 2x3 plus 2x4 is equal to 3. My screen isn't sharing. Thank you. Let's see. Share screen. Why isn't this working? I see it on my screen. Yay. Okay, now you can see. Now is it good? Okay. Awesome. So here we have this system of equations, and we are told that the determinant of A is equal to 120, and we are asked to use Kramer's rule to solve for x3 only. So we're asked to find the determinant of A sub 3. So a great way to start this problem, to make sure that you get at least 1 point for it, or half a point, or however many points it's worth, x3 is equal to the determinant of A3 over the determinant of A. Let's say that you don't get the determinant, or you're like trying and struggling and you can't find it. Writing this down is a great way to get some part marks, showing me that you know the formula. Okay, so now x3 comes from replacing the third column with 2533. So what this would mean is 1, negative 1, 5, 3, 0, 0, 2, 0. Now instead of the third 2, 10, 4, negative 2, I replace it with B, which is 2, 5, 3, 3. And then I have 3, negative 1, 3, 0, negative 1, 2. Now, I've been talking about efficiency and a good way to approach these problems. Well, things that I've seen you guys do on the tests and on your labs is to look at this and be like, I'm going to use this 1 right here. and I'm going to make zeros. Does that seem like a good plan? No. I have a whole column of zeros. I'm going to use column 2 here. So I'm going to use column 2, and I'm going to make my plus minus matrix. So plus minus plus minus, minus plus minus plus, plus minus. So that 2 is in a minus place. Now notice I have straight lines because I'm saying this is the determinant. I want to know what this equals. So I pull my minus 2 out front. I don't have to worry about the rest of the stuff because it's just going to be multiplied by 0. I cross out the row in the column with the 2, and then I end up with a 3 by 3. Exactly. So now I have options. I can use the 3 by 3 trick, or I can keep row reducing. A thing that you should not do is cofactor expansion. Cofactor expansion at this point is the longest method. And so this is another thing I saw you guys doing cofactor expansion, but not even picking the row or column with the 0, saying, oh, look, I'm just going to do cofactor expansion on the first column and having to find 3 different cofactors. That is a massive waste of time. It is creating so much extra work that you do not need. So at this point, you can choose. You can do the 3 by 3 trick, or you can do more row operations. I find it easier to do the row operations in my head, but either one is good. And because I don't have a calculator, I'm just going to do the row operations. So I'm going to do row 2 plus row 1 and row 3 minus 3 row 1. And that's going to give me 1, 2, 3, 0, 0, 7, 3, 3 minus 6, that's negative 3, and then 2 minus 9, that's negative 7. Then I'll do cofactor expansion again. I'm going to do my plus minus matrix. That's in the plus place. So then I'm going to do cofactor expansion down the first column. The 1 is in a plus place. I forgot to write the negative 2, but it's still there. So this is negative 2 times positive 1 times 7, 3, negative 3, negative 7, which gives me negative 2 times negative 49 plus 9. And I got that the determinant of A3 was positive 80. The 3 by 3 trick, like I said, is also a perfectly reasonable way to approach this problem. So then my x sub 3 is equal to the determinant of A3 over the determinant of A, which we were given. So x3 is 2/3. And that's my final answer. And notice that did not take me a lot of space. It also did not take me a lot of time. Number 9. Already move on? It's vector time and planes and lines. I can pick the column, any column I want. So in this case, I picked the first column in that 1 because the 1 was there and it was easy. I also could have picked the third column, except the third column would have been a little bit more challenging, even though it has a 0 in it already. To find the row operation, I would have had to do like row 3 minus 2/3 row 1. So I would have had to bring in fractions. I haven't looked at May 2019. I'll go back and look at it, but I mean, it might be more challenging because some are definitely easier than others. I'm hoping that yours is a mixture, like a reasonable thing. But as of right now, like all of these problems are pretty standard. Like all of these problems are pretty standard as to what you can see show up. Now, outside of this, like as of right now, for example, we did this question right here, and this one is maybe a little bit on the more challenging side because it really requires you to remember that thing. But other than that, I think that most of these have been pretty standard. My guess is it's going to get a little more challenging when we get into the vector section. So Number 9, we're given 2 lines. L1 is xy is equal to 2, 4 plus s times 3, 1. And L2 is equal to xy is equal to 1, 2 plus t times -1, -3. Why didn't I pick row 2? You mean for cofactor expansion, Daniel? Because it had 2 zeros. How many zeros did column 2 have? Yes, that's why. Okay, so A here says, are the lines parallel? Well, to see if they're parallel, we just have to compare our direction vectors. Are these scalar multiples? They are not. On the test yesterday, I had these things. I think it was like this, maybe. A lot of you said that these were not scalar multiples. So the zeros maybe are the thing that confused you because it starts off with 0, so you couldn't figure out what to multiply by. If those zeros are there, just move on to the next thing. So I'm doing -5 and 3. So I have -5 over 3. So that means -5/3 here. Are these two things equal if I multiply by -5/3? Yes. So they were scalar multiples, and unfortunately that changed a lot of stuff for you guys. So be careful about scalar multiples. Just because it doesn't look exactly like you expect it to, sometimes you might have to multiply by something like -5/3. Always do one component divided by the associated component. So here, it would be multiplying by 1/3. So here I would be like -1/3. So -1/3 times 3, 1 does not equal to -1, -3. So no, they are not parallel because their direction vectors are not scalar multiples. Okay, B. So B says, are they perpendicular? What do I need to check to see if they're perpendicular? Not the cross product. The cross product will give me a new vector, plus the cross product only exists in R3, and we're in R2 here because these vectors only have 2 components. So, I mean, that's kind of one way to look at it. But the general way to look at it would be, does the dot product equal to 0? So I think that none of you are probably thinking the right thing. Perpendicular if the dot product equals to 0. So does the dot product of the direction vectors equal to 0? And so here I'm going to do 3, 1 dot -1, -3, which gives me 3 times -1 plus 1 times -3, which is equal to -6, which is not 0. So no, they are not perpendicular. So if I have 2 lines and they're not parallel and they're not perpendicular, how many times do they intersect? Think about it. Imagine two lines in your head, two lines on a piece of paper. If I have two lines, draw two lines on a piece of paper. If they're not parallel and they're not perpendicular, how many times do they intersect? Draw pictures, guys. Good job, Daniel. Good job, Judy. I have two lines, guys. They're not parallel and they're not perpendicular, which means maybe they look like this. Remember, lines go on forever. Hands down, they're going to intersect exactly one time. They're going to look like that. If they both pass through the origin, we don't know if they pass through the origin. All I know is that they're not parallel. And if two lines aren't parallel, then that means their slopes aren't the same, which means that hands down, they're going to touch one time. Two lines that aren't parallel will always intersect one time. Okay, next question. And hang on, maybe I'll draw a picture for you guys real quick instead of, if I have this line, and then I have this other line that's not parallel to it, notice if I just keep drawing, eventually they have to touch. Can they touch more than one time? No. So they're not going to touch infinite times. To touch infinite times, they'd have to be parallel. They'd have to be the same line. To touch no times, they'd have to be parallel and not the same line. Okay, number 10. So I notice a few of you that are here still haven't participated at all, and I just want to remind you that I am looking back at the chat and making sure that you're consistently participating throughout the whole thing if you want to get your bonus points. Don't want anyone to be like, but I was there. I'm keeping the chat. You have to be participating, answering questions, asking questions. So here we have A is equal to 3, negative 2, 4. And V is equal to negative 2, 5, 1. How's that, Adam? Exactly-ish. So I'll just remind you, the vector between 2 points, this is saying that B is going to be my initial point. So I'm just going to start off by saying B is going to be, oops, uh-oh, what just happened? No. B is going to be equal to, let's just say that B is X, Y, Z. Then BA, we know, is A minus B. So this is 2 minus, I don't know where that 2 just came from. I'm just making numbers up here. Is A minus B. So this is 3 minus X, negative 2 minus Y, and 4 minus Z. And I want this to equal to V. So A is a point, V is a vector, and now BA we have, and we're setting it equal to negative 2, 5, 1. So in other words, 3 minus X is equal to negative 2. This means X is equal to 3 minus negative 2. which is 5. Negative 2 minus y is equal to 5, which means y is equal to negative 2 minus 5, which is negative 7. And then 4 minus z is equal to 1, which means z is equal to 4 minus 1, which is 3. And so now we have our point, b is equal to 5, negative 7, 3. Let me look at the next thing here. Oh, how did I do that? So the thing that I know is BA or AB, so like if I want the vector between 2 points, I'm always doing the B component minus A component. So I always do the terminal point minus the initial point. So this right here is BA, which means this is A minus B, A minus B, A minus B. And that's because A is my terminal point. And then I know what I want this to equal. I want it to equal negative 2, 5, 1. So I just created 3 equations doing that. Does that make sense? No. AB would be B minus A. So BA is A minus B. So AB would be, if I wanted AB, if I wanted to solve for AB now, it would actually be 2, negative 5, negative 1. So it would be the value flipped. And some of you have messed this up. You've done initial point minus terminal, but it's always terminal minus initial. B. Find a vector equation for the line through A that is parallel to B. So I know for my vector equation, I'm in R3, so I have x, y, z. You got it, Alex. So x, y, z is going to be equal to a point plus t times a direction vector. So this is going to be a point, and this is going to be a direction vector. And we know that direction vectors are parallel. So in other words, I'm drawing a line, and I want this vector parallel to it. Well, v is parallel. So that means v is going to be my direction vector, and a is a point. So in this case, it's pretty straightforward. I can just write down the answer. A was 3, negative 2, 4. And v was negative 2, 5, 1. So then we're going to be given a point and ask if that point is on this line. Well, that depends, Nick. That depends on what type of equation you're trying to write, what information you're given about V's relationship to the line. So there is never always in the equations of planes and lines. It really always depends on the circumstances and what's being asked in the question. I know that's not the best kind of answer, but unfortunately with planes and lines, that is kind of how it is. You really have to. How would you do B if it was perpendicular? Then you would need a vector that was perpendicular to negative 2, 5, 1. So you would be looking for a vector that negative 2, 5, we'll call this vector in, 5, 1 dot in is equal to 0. So in other words, you would need to find a vector such that that is true. So negative 2, 5, 1 is your direction vector because we are told that B is parallel. It's not the cross product, Daniel, because I only have one vector. So I can't do the cross product of two things if I only have one thing. Excuse me. Sorry about that. So negative 2, 5, 1 is our direction vector because we know that a direction vector, what it means is for that vector to be parallel. Thank you. The vector has to be parallel to the line. So the direction vector can be any vector that is parallel to or on the line. And here we're told that B is parallel to the line. So that's why it's our direction vector. Okay, now I want to know if negative 183 is on the line. Now we've said it's useful to write this in parametric form. So in other words, I'm looking for t such that 1 is equal to 3 minus 2t. I'm sorry, negative 1. 8 is equal to negative 2 plus 5t. And 3 is equal to 4 plus t. So this would tell me that 2t is equal to 4, which would give me that t is equal to 2. It would tell me that 5t is equal to 10, which would again give me t equals 2. But here, what t would this give me? Good job, Nathaniel. Exactly, this would give me negative 1. Are all of these the same? No, so these are not all the same. C is not on the line. But negative 1, 8, if I plug in t equals 2, if I replace that 3 with a 6, it is. So in other words, if I said, well, if t were equal to 2, plug that in, what value would I get? I would get negative 186. Okay, D. Let U equal, oops. Find a general equation for the plane P through A with vectors U and V that lie on the plane. Okay, so I will be sending you a mail later today. I kind of want to just check a couple things, but I'll send you an MIO later today. Depending on how long I talk to people after class, will depend on when, but it seems likely that the exam will go live at 8:55. possibly 8:50. Yes, till 12. And then you'll have 20 minutes to submit. Okay, so here we are given, I'm just gonna draw a picture. We're a plane, and I'm like, I know this point A is somewhere on the plane, and then I know the vector U is on the plane, and I know the vector V is on the plane. Yeah, exactly, Jake. So I want a general equation for the plane. So what does a general equation look like? It looks like AX plus BY plus CZ is equal to D. Now, one of the things that I've noticed from talking to a lot of you is that you don't know what the word normal means. And you don't know that when you look at this, I can get this vector right here. The vector that comes away from this, ABC, is the normal vector. And that the normal vector is orthogonal to the plane. And what does the word orthogonal mean? Yes, Kyle, exactly. Orthogonal means perpendicular. So this normal vector is perpendicular. So this normal vector, in other words, cannot be U or V. U and V are on the plane, so they are direction vectors. Which means I need this third vector that's a normal vector that's sticking out of the plane. Oh, I'm sure they did. They're just not saying anything. So the normal vector would be then the cross product of the two direction vectors. So my normal vector would be D1 cross D2. But in this case, that's U cross V. So my normal vector is equal to U cross V, where U is 0, 2, 1, cross V, which I don't remember, so I gotta go back and look at it, V, negative 2, 5, 1. Cross out the first column, and I get 2 minus 5, that's negative 3. Cross out the second column, I get 0 minus negative 2, that's positive 2, that I multiply by negative 1. Cross out the third column, I get 0 minus negative 4, so that's positive 4. This is my normal vector. So then I have negative 3x minus 2y plus 4z is equal to d. So you might have noticed on the practice solutions, I plugged it into the point normal equation. But note that we can also just plug in the point. So our point is 3, negative 2, 4. So now I plug in A is equal to 3, negative 2, 4 to find D. So this is negative 3 times 3 minus 2 times negative 2 plus 4 times 4 is equal to D. And I get negative 9 plus 4 plus 16 is equal to 11. So my plane is negative 3x minus 2y plus 4z is equal to 11. Is A negative 3? No. So that's my A. My A is positive 3 there. So I'm plugging in 3, negative 2, 4. Okay, So then the last question is I want to find a unit vector that is orthogonal to the plane. And that is E. Well, my normal vector we know is already orthogonal to the plane. So n is equal to -3, -2, 4 is orthogonal to P. So now I just need to make this a unit vector. So to make this a unit vector, first we find the magnitude. And that gives me the square root of 29. So I did -3 squared plus -2 squared plus 4 squared, which means that my unit vector, which I'll call u sub 1, I could multiply by 1 over root 29 or -1 over root 29 to get the opposite direction. So this gives me -3 over root 29, -2 over root 29, and 4 over root 29. And that's my final answer for this. Are there any questions about this one? What do you mean plus? Oh, because it only asks for 1. So it only asks for, so first of all, when I do that square root is the magnitude. So it's the length of the vector. So we only take the positive square root when it's the length of the vector. So the magnitude is always positive square root. We're not going to have a negative length. Okay, but then that said, this gives me a vector in the same direction, and we were only asked for 1 unit vector. If we were asked for 2 unit vectors orthogonal, then another one would be to multiply by -1. Possibility would be -1 over root 29 times this. So this would give me another unit vector, and it would be, so if one is orthogonal like this, like pointing towards it, can you guys see that? If one is orthogonal pointing towards it, then the other one would be orthogonal pointing away from it and be a unit vector. So that would also be a valid possibility. Did that answer your questions, Nick and Cody? Okay, give the equation in vector form of the intersection of these two planes. In vector form, oops. Of the line of intersection of x plus 4y plus 2z is equal to 4 and 3x plus 13y plus 5z is equal to 10. Okay, so how do I do this problem? I want the intersection of these two planes. How do I find the intersection of planes? You put them in a matrix, right? This is actually the same as this question right here. It's the same as 1a. It's just asked a little bit differently. What did I do when I solved this? I put it in a matrix and I solved. I found the intersection of the 3 planes. Well, now I want to find the intersection of these two planes. How do we find the intersection of the two planes? We stick them in a matrix and we row reduce. So this is the same as 1A. It's just asked a little bit differently to make sure that you understand the vocabulary. So then I will do row 2 minus 3, row 1. 1, 0, 4, 2, 4, 13 minus 12, that's 1, 5 minus 6, that's -1, 10 minus 12, that's -2. And then I will do row 1 minus 4, row 2, which gives me 1, 0, 0, 1, 2 plus 4, that's 6, -1, 4 plus 8, that's 12, and -2. How many free variables do I have? 1. Good news, because we were told it's a line, so we should only have 1 free variable. We're told that the intersection is a line. So that means we have 1 free variable. We define all of our variables. X is equal to 12 minus 6t. Y is equal to -2 plus t, and z is equal to t. This is my parametric equations. We were asked for the line in vector form. So now I'm going to take those parametric equations and write them as in vector form. The point is 12, -2, 0, plus t times my t vector, -6, -2, 1. And this is your final answer. Are you guys ready to move into spans? It's not -2. Oh, I'm sorry, it's 1. You're right, my bad. 6, 1, 1. Thank you, Alex. Because it's spans time. Parametric and general equations are totally different. Parametric and vector equations are the same thing. Like a general equation is ax plus by plus cz equals d. A vector equation and a parametric equation is like point plus t times direction vector. Does that answer your question, Mark? The general solution, and this is a thing that I was talking about earlier, general solutions and general equations are not the same thing. So these right here, these are the general solution, but they are not general equations. These are the general solution in a vector and parametric form. So a general equation is a type of equation. A general solution is a solution that represents all of the possible answers. Does that answer your question? We can't do a general equation of this. Oh crap, hang on 2 seconds, guys. Exactly, exactly. So we can say here, no general equation of this line. Because it is in R3. Exactly, so general equations in R3 always represent planes. Are there any other questions about this? So moving on to 12. We're given some vectors. You don't hear me, Drury? I don't know what to say. Okay, so we're given these vectors, and the first question is, are they linearly independent or dependent? So the answer is that I can't look at them and tell. I have to row reduce. So I have two options here. I could take the determinant or I could just row reduce. But the second question is asking me what they span. So I'm going to actually row reduce here. It's 3 vectors, so we have to do something. We have to do work. Okay, so I'm going to stick these in a matrix, and it doesn't matter what order I put them in. Exactly, it does not matter what order I put them in a matrix. So what order do you guys want to put them in? What order looks like a good order to you guys? So I think VUW is also kind of a good order, or I could do WVU. We'll go with a VUW since that was what was suggested. And then notice I can easily just multiply the first row by a half to make that first number a 1, because there are only 2. Because it doesn't matter. All we need to know is if there is a useless vector, right? So what I'm doing here is I'm saying C1 times U plus C2 times V plus C3 times W is equal to 0. But it doesn't matter if I do this instead. Right, so like it's basically just saying, how can I write these as a linear combination of each other? It doesn't matter what order I put them in because I'm finding constants to go in front of them. And if I do C2V first as opposed to C1U first, it doesn't change anything. It just changes which constants are associated with which vectors. And to go into more depth about that explanation, we actually spent a little while like looking at equations and talking about it in class. And it takes I could go into more depth, but it would take a long time. So I think I'd rather just kind of do the problems. Okay, so then I'm gonna do row 2 minus row 1 and row 3 minus 4 row 1. And I get 1, 0, 0, 0, 1, 1, negative 1, 3, negative 3. And then notice what happens here. Those last 2 rows are scalar multiples. So if I do row 3 minus 3 row 2, I end up here. Is it better, Druby? Are you hearing now? Yay! How many pivots do I have? 2. So are these dependent or independent? You got it, Jake. These are dependent. So the answer here is linearly dependent. Now this is a place where some of the best students even messed up on the test. So let's really like talk about the second question. So the second question, what is span of UVW? Write an equation for it. Write an equation, write a vector equation. Find a basis. Actually, we'll do that. We'll do that second. Okay, so what is the span of u, v, and w? Is it a point, a line, a plane, or the whole space? You got it, Jake. It's a plane. Those two pivots mean two independent directions. So I'm no longer looking at the solutions. I'm no longer looking at my free variables. I'm looking at the number of pivots. So this is two pivots, so two directions. Span is a plane in R3. And the equation for that plane does not come from the solution. It comes from getting rid of the useless vector. Well, in this case, the useless vector we're getting rid of is 2, 0, 1. So my xyz would be equal to t times 2, 1, 4 plus r times 0, 1, 3. The point is the origin because it's a span. And I just got rid of the useless vector to write my equation. We know that spans are lists of direction vectors. Yes, that is what you did wrong. If I wanted a general equation for this plane, I would do the cross product of those two vectors to get my normal vector. Now C, the question is true or false? Span u, v, w is equal to the span of u, v. Is that true or false? It doesn't matter, Andrea, because u and v aren't scalar multiples, right? So yes, our useless vector that we got rid of there was, it depends on how much time I have. It seems unlikely I'll have time to, because it takes a while to get them to send to my computer. So it seems unlikely, but I'll try to post the video. So the answer here is true, because what we saw is that these are linearly dependent, and there is one useless vector. Since none of them are scalar multiples, it doesn't matter which vector I get rid of. We can write W as this. Yeah, so like I could also say that this is true. Right? Like we only need two vectors to cover the space. So in other words, W is in the span of U and V because I can write it as a linear combination of those things. U is in the span of V and W. V is in the span of U and W. It doesn't matter. Like the vectors are all in the space. And therefore that UV, so I'm going to add a question here that's not on the test just because like you guys struggled with this. Find a basis for the plane from B. So a lot of you said, there is no basis. The vectors are linearly dependent. No, that's not what that means. When it says to find a basis, what that means is get rid of the useless vectors. So a basis here would be like UV. Or with what we did, we'll have UW. That's my basis. They're linearly independent and they span the whole plane. If I put a span in front, then suddenly that's the wrong answer. So like some of you also did this. You put the word span right out there. The basis has 2 vectors in it. The span is the whole plane. It has infinite vectors in it. So the basis is just those 2 vectors. If we put this word span out front, it's wrong. $13. Nope, if you said UV, that would also be totally fine because it's 2 linearly independent vectors that span the whole space. So that's another basis. Remember, we also said that bases are not unique. There are often lots of different bases that you could give. Okay, so here you're given 2 sets, and we're asked which one of the 2 sets is a subspace. What's the answer? We should be able to look at this and know the answer. Yes, Bert, good job. Anyone else? Good job, Daniel. Well, let's start off with the 0 vector. So S1, 0 plus 0 minus 0 equals 0, and 0 minus 0 plus 0 equals 0. So it's there. S2, 0 squared is equal to 0 squared. They both contain the 0 vector. So that brings us to the second step. Which one is a linear equation? In S1, do we have linear equations? Yes. So here, these are linear equations. What about over here in S2? Do we have linear equations? No. So S1 is the subspace. If we're told that one of them is a subspace, it's got to be S1. It's linear equations. So then we want to provide a basis for that subspace. We stick it in a matrix and we row reduce. So it's the intersection of these 2 planes, which is probably a line. So I will do row 2 minus 2 row 1. Okay, I just want to point out, I know I've said this like 1,000 times already, but there are people that have been here the whole time that haven't said a single word. And if you haven't said a single word and you haven't been participating, then you will no longer have the option to get the bonus points. Just want to be clear about that. Okay, so then I'm doing, I get a 0 here, -3 minus 2, that's -5, 14 plus 6, that's 20, and then we have 0. So then I'm doing row 2 times -1/5, 1, 1, -3, 0, 1, -4, 0, 0. We have one last row operation to do. Row 1 minus row 2. will give me 1, 0, 0, 1, -4, -3 plus 4, that's 1, 0. Okay, so now I have my one free variable. You don't have to put the column of zeros. No, it's not a big deal if you don't. Like, they change nothing. That's just the point. So then I get my one free variable we're going to call t. So I get x is equal to -t, y is equal to 4t, and z is equal to t. So then my basis is just my t vector, -1, 4, 1. Okay, B. Which is not a subspace. No, the basis of a span is getting rid of useless vectors. Here we had general equations, right? So we've seen how do you rewrite a general equation as a span? You put it in a matrix and you row reduce, right? So like when we're thinking of bases, usually the first thing that we want to do is write it as a span, right? So how do I write this as a span? I stick it in a matrix and I row reduce. So technically I could even say here that S1 is equal to the span of this vector. Now I would get rid of useless vectors, but there aren't any, right? So first, when we're dealing with bases, we get the span, then we get rid of the useless vectors. If we're given a span to start, then finding a basis is ultimately just getting rid of useless vectors. Yes, that's why subspaces are a little bit challenging. No, you don't need to go on Zoom tomorrow. So for B, it says, which is not a subspace, provide a counterexample. Oh, and then we write S1 is a subspace. A lot of you did not tell me what this means. I need to know that you know that connection. So which one is not a subspace? So we know that in S2 is x squared equals z squared. So the first thing we're going to do is make a list of vectors. Now, a lot of you did not make lists of vectors for me. You just wrote like 4 squared is equal to 4 squared. That's not a vector, right? We need to write actual vectors in R3 with the property that x squared is equal to z squared. So our property here is that x squared is equal to z squared. So give me some vectors in this space. (202) would be in the space. Good job. And the reason this is in the space is because 2 squared is equal to 2 squared. Now, give me another vector in the space. And let's try to be creative here. -5, 55, 5. -4, 0, 4. You got it. So both of these are in the space as well because -5 squared is equal to 5. -4 squared is equal to 4. If it asks you to write it, yes. If it doesn't, like it did on the test, it specifically asked you. Good, Ben. So now we have a fraction 1/7. 1/7, except I'm going to change this to like a -2, 1/7. So 1/7 squared is equal to 1/7 squared, squared, squared. Okay, now we want our counterexample. So for our counterexample, we're going to look for either scalar multiplication or vector addition. But what I see here is that scalar multiplication is not going to work. No matter what I multiply by, it's not going to change the fact that the x and z values are the same number. So we're going to think about vector addition. Because I was creative, I have negatives and positives. So if I do 202, which I know is in the space, and I add to it -5, 55, 5, I end up with -3, 55, 7. This was in the space. This was in the space. Is my new vector in the space? Is it true that -3 squared is equal to 7 squared? No. So this vector is not in the space. The space was S2. So S2 is not a subspace. And that's my final answer here. Okay. Are there any questions about this? Okay, it is 11:50. I definitely want to do at least the next 2 questions on this test, just because I think they're important in terms of the things that you guys have been struggling with. After that, though, it goes into like the null space and the column space, and then the word problems. So even if I go over, you do not make up any numbers for a counterexample, Adam. You specifically start with vectors in the space. So your vectors have to be in the space to start. Right? So over here, I found vectors that were specifically in the space. And then I found a way to add 2 of them together to escape the space. Yes, that's fine, Daniel. In this case, the y in the vector can be anything because the only condition is that x squared has to equal to z squared. Okay, so I definitely want to do the next 2 questions on this test. After that, if you guys want me to stick around and do a few more problems, I can. I'm going to have to leave at like 12:20 at the latest, though. And then I know I'm supposed to meet with some of you. So after 12:20, I'm just going to talk to you guys, the ones I'm supposed to meet with, to pick times later. But from like 12:20 to 1, I will not be available. But I am going to quickly do the next 2. So 14. Adam, I've been trying to open it. I think it might have worked finally. So we can look at it. So number 14 is we're given a space. S is equal to a vectors in R4 such that x1 plus 2x3 is equal to x2 plus 2x4. And we're told it's a subspace. A, find a basis. And we know to find a basis, yeah, that's fine, Dick. To find a basis, we first want to find a span. And we know that spans are lists of direction vectors. What I have here, if I were to rewrite it, and remember we said that we kind of want to write things horizontally with everything on the left. So I have x1 minus x2 plus 2x3 minus 2x4 is equal to 0. What I have here is a general equation, which means I have a normal vector, not a direction vector. And so Parth, maybe this will help where you were being confused before. Spans, which I need to get my basis, are lists of direction vectors. So how do I get direction vectors? I stick it in a matrix and I row reduce. So I'll have 1, -1, 2, -2. I can augment with 0 or not. So basically it's like I'm finding the null space of this thing. So then I get that x1 is equal to, I have 3 free variables here, t, r, and s, is equal to t minus 2r plus 2s, x2 is equal to r, I'm sorry, t, my bad, x3 is equal to r, and x4 is equal to s. And now I can see that I'm going to have 3 vectors in my basis. T vector, R vector, S vector. So the space is the span of those 3 vectors. So S is equal to the span of my T vector, which is 1, 1, 0, 0, my R vector, and my S vector. That's not my basis though, because it has the word span in front of it. That's an infinite amount of vectors. They're linearly independent because I got them from row reduction, so I don't have to get rid of any useless vectors. My basis for S is just those 3 vectors. Are there any questions about how we just got that basis? So then the dimension of S, what's the dimension of S? It is linearly independent. If you have done things right and you've row reduced to get this, then you'll always end up with linearly independent vectors, right? If you're given a span to start, if you're like span of a whole bunch of vectors, you don't know. But if you've row reduced to get them, they should be linearly independent. So the dimension is 3. Okay, 15. It is possible. So like, for example, if we go back up to this problem right here that we did, where we had 3 vectors, and we were like, let's think about the span of those 3 vectors. So the span of those 3 vectors was a plane. So then we were like, let's find a basis for that span. The basis only contained 2 vectors because we had a useless vector in there. So if what you're given is like a set of vectors and a span, then sometimes you'll have useless vectors to get rid of. However, if you're doing something like row reduction to turn the general equation of a plane into a vector equation, or the general equation into a vector equation, which is what we did here in 13, and what we just did again in 14, then you'll always end up with linearly independent vectors. Did that make sense? Okay, 15. So 15 says, write a matrix in Rref whose column space is 3-dimensional and whose null space is 2-dimensional. Or state that no such matrix exists. So here we have to write a matrix. You got it. So it's going to have 2 free variables. It doesn't necessarily have to be 5 by 5. It could be a different size, but it does have to have 5 columns. So I could have like a 7 by 5 or 12 by 5 even, but it has to have 5 columns because this is telling me that there will be 3 pivots. And this is telling me that there will be 2 free variables. So my matrix, for example, could be 1, 0, 0, 0, 1, 0, 0, 0, 1. Notice I'm not in R5 here. I'm in R3. So this is 3, but now I need 2 free variables. So I could have 2, 5, 6, 3, 4, 9. And notice the matrix I made was not 5 by 5. It was 3 by 5. I could have had 2 rows of zeros and that would have also been fine. Wow, it's 12. Okay, so it's 12. Do you guys, you can go now if you want, you can stay if you want, it's up to you. I'm gonna do a question that Adam had asked earlier, and then if you guys want to stay and you ask, like have, let me see if I can find the question Adam asked. If you want to stay and ask more questions, I'm happy to, like I said, stick around for the next 20 minutes, and I can do more. Okay, Adam, I'm trying to open the question. Mike. So yeah, hang on. Let me respond to these things. Spike field. And then okay, hang on. Let's see. My computer is being slow, but I think I have it. Okay, so I don't know how to share this with everyone because it's on my computer. So this is really similar to what we did. I think the best thing, actually, I'm gonna stop recording. And okay, so we have A reduces to R, which gives us this. And then the first question is, which of the following sets are a valid basis for the column space? And the first set that we have is, and we'll just go set by set here. Actually, no, we'll, is this. And then oh, that's it. Okay. So how many vectors does, how many pivots does R have? It's got 2 pivots, you got it. So I've got 1 pivot there, and I've got 1 pivot there. So what that means is I just need 2 linearly independent vectors in the column space. So 2 should be pretty straightforward. Oh, uh-oh, my phone's ringing, which means I can't go back and look at the problem. So what that means is I need to see, if I take the row reduced form of these, will I have 2 pivots? So 3, 2, negative 4 reduces to 1, 0, 0, and 3, 1, 19 reduces to negative 4, 3, 0. Do I have 2 pivots? Yes. So this then is a good basis. Now what about 1? Are those vectors in my column space? Hang on, I'm rereading the question. Oh yeah, okay. So for this one, these vectors are from R, not from A. To be in the column space, we're looking at A, we're not looking at R. So these vectors are not a basis, they're from R, not A. So my answer here is just 2. Does that make sense? So when we think about what the basis for the column space is, I don't say, oh, let's take the vectors from, like I say, okay, the pivots in R are 1, 0, 0, 0, 1, 0. Let me take the associated vectors from A. We always go back to A to find our basis for the column space. We're not looking at R. B, what is call A? Well, we just said that there are two pivots, there are two vectors, so what does two vectors span? You got to take a plane. A plane in what space? How many components are in the column vectors? 3. So the answer here is a plane in R3. Because rank is 2. Exactly, exactly. We're looking at the number of rows to find where the column space is. Okay, so then the next question is C. Write 319 as a linear combination of 3 to negative 4 and 5, 3, 1. So many of you tried to use A in row reduce. That is not what we do here. If the rank was 1, it would be a line in R4. 1 vector spans a line, 2 vector spans a plane. Okay, so this, we're saying I want to write 319 is a linear combination of these things. Actually, I need to keep seeing R. So I'm taking from R, I'm taking the values from R, row reduced, and I'm replacing 3, 2, negative 4 with its row reduced form, 1, 0, 0. I'm replacing 5, 3, 1 with its row reduced form, and I'm replacing 3, 1, that should be a 19, huh? It is, okay, sorry about that. And I'm replacing 19 with its row reduced form. Perfect, it's already in our Rref. So no row reduction is necessary. Okay, so wait, hang on guys, 2 seconds. Okay, so what this means is my C1 is equal to negative 4 and my C2 is equal to 3. So this tells me I go back now to the original vectors, 4 times 3 to negative 4 plus, I'm sorry, negative 4 plus 3 times 5, 3, 1 is equal to 3, 1, 19. We didn't have any work to do. We literally just stuck it in the matrix. We stuck it in the R matrix. We just extracted the vectors from R. Next, find a basis for the null space. How many variables are there? Five, you got it, with 3 free variables. So hands down, I know before I even start that I'm gonna have 5 components here. So I'm gonna write down all 5 of my variables so that I don't accidentally forget to define some of them. So x1, now I'm gonna have t, r, and s. So minus 3t minus 2r plus 4s. Then x2 is just t, because it's a free variable. Go back to the matrix. x3 is minus r minus 3s. And then these are also free variables. So now I have 3 parameters from my 3 free variables, 3 vectors in my equation. Those give me my basis. So I have my t vector. I have my r vector. And I have my s vector. And that's my final answer to D. E. What's rank of A transpose? If you were to give, so the question is in A, why is the second vector not the one with the pivot? Because bases are not unique, right? So if I were to ask you, write a basis for the column space down, you would probably write 3, 2, -4, 5, 3, 1. But then remember that a lot of times I ask you, find another basis for the column space. And what you're using to do that is you're saying, well, this basis has 2 vectors in it. And those 2 vectors are linearly independent. They have 2 pivots. So you just need to find any 2 vectors that have 2 pivots, and that will act as a basis for the column space. So 2 is just another basis for the column space. Another basis I could give for the column space would be if I were to do, for example, 9, 6, -12, comma, 11, 7, -7. Because if I extract those 2 vectors, I still have 2 pivots. So these are other bases for the column space, right? So they're asking you, is this a basis? They're not telling you to present one. All right, what's the rank of A transpose? You got it, it's 2. And this is because we know that rank A is equal to rank A transpose. And then the last question is, what's the nullity of A transpose? A is a 3 by 5 matrix. You got it, guys. It's going to be 1. So A is 3 by 5. So A transpose is 5 by 3. And we know from E it has 2 pivots, which means there's 1 column left over to be a free variable. So the nullity of A transpose is equal to 1, which, by the way, based on what we did on the test, this means A transpose X equals 0 has 1 free variable or parameter. All right, guys, it is 12:17 and I gotta go. Any last minute questions here?